Good afternoon, everybody, and welcome to this third lecture of our MIT Energy Initiative Seminar Series. Today we have the great pleasure to welcome Stephen Selkowitz from the Lawrence Berkeley National Lab. But before I introduce the speaker, I would like to first of all ask all of you to switch off all of your iPhones, Blackberries, any kind of cell phone. We also have a video facility here, and it may even create interferences, so thanks a lot. I would also like to thank the CERA, the Cambridge Energy Research Associates, for being the sponsors of this seminar series. CERA recently joined the MIT Energy Initiative that we call MIT, so it's a little pronunciation thing. If you say MIT, you mean MIT, but if you say MIT, you actually mean the MIT Energy Initiative. So get used to it. They are sponsoring this seminar series for this entire year, 2008-2009. They are a consulting company specializing in advising international energy companies, governments, financial institutions, and technology providers on energy markets, on geopolitics, on industry trends, and on strategy. So they have a pretty broad portfolio, and their expertise covers all major energy sectors, ranging from oil and refined products to natural gas and electric power, on both a global and a regional basis. They have offices in North America, Latin America, Europe, and Asia. So thanks a lot, CERA, for sponsoring this event. And I also wanted to point out that this lecture will be followed by a reception at the back of the room, and you're all more than welcome to join us for this reception. A little note about the upcoming lectures for this MIT seminar series. On December 2nd, we will have George Crabtree from the Argonne National Laboratory, who will talk to us about the sustainable energy challenge from a material science perspective. And then we will, it's usually a monthly series, but we will jump over January, which at MIT is an independent activity period, and go all the way to February with Jean-Marie Tarascon, who's a professor at the Université de Picardie Jules Verne. My French accent is because I have a bad accent in English, so I'm a French-speaking faculty who's member of the French Academy of Science, and he'll talk to us about recent advances, new trends, and future challenges within the lithium-ion battery energy storage system. And then following up, we'll have lectures in March, April, and May, and that will close our entire MIT seminar series. So today we have Stephen Selkowitz with us, who will tell us his view, and I hope it will raise an exciting discussion afterwards about zero-energy buildings and more generally the impact of energy efficiency in buildings and of buildings in general in the energy picture today. Stephen is the department head of the Building Technologies Department at LBNL, and I would like to borrow from the ACEEE, the American Council for an Energy Efficient Economy, a description of Steve. He was named champion for energy efficiency by them in 2002, and they called him a tireless, persistent, gently persuasive, we'll see if it's that gently, and innovative, that's definitely true, leader, that's definitely true as well, in the energy efficiency R&D field. So this sort of, I guess, sums up who Stephen Selkowitz is. His group is about 70 or more people, researchers in all kinds of areas related to buildings, windows and daylighting, lighting systems, simulation research, energy, commercial building performance, demand response research, and many more. His area of expertise goes all the way from basic materials research to energy simulation tools, and he'll talk to us more about what he's doing. He's been publishing over 170 publications, 3 books, 2 patents, so he's definitely a leader in this field, and we are very honored to have him speak to us today. So without further me speaking, I'll get him to talk to us. Thanks a lot, Steve.
Yeah, noise, sound. Here we go. Okay. Sorry. Have to master the controls first here, right? Thank you, Marilyn. It's a pleasure to be back here. As I'll hint in a minute, I actually grew up in this area. Grew up in Newton, went to Harvard as an undergrad, so there's some fond memories of this part of the world back. But even more interesting, it's a great time to be in the energy world. I've been doing this for more than 30 years, and a lot of that time has been a real struggle, but things seem to be changing a bit for the better, which is always interesting and positive and optimistic. Before I start, I want to get a sense of the audience, and I realize it's a diverse audience. How many people here work directly with buildings or energy use in buildings one way or another? 2/3 of the group. Okay, great. The other thing is I'm going to go through a lot of material quickly. I will figure out a way to post this so you can download the presentation if you'd like. I'm not going to try to cover all the material on every slide. It'll take until tomorrow morning. I think it's probably better to sort of run through a lot of these arguments and issues at a higher level and then leave the details for later. But I'll try to leave a half an hour at the end for Q&A and can pick up any of them at the same time. Oh, just to prove that I'm a real Bostonian here. I get beat up at times in the Bay Area, but anyway. So let me just jump in here. So briefly speaking, I'm going to sort of start from the big picture and work down to buildings, work through the U.S. energy picture and work to buildings, and then I'm going to look at this issue of zero energy buildings. I'll come back and define it a bit better later, but basically this is really all about aggressive energy savings in buildings. And I'll illustrate it really more by talking about the work that's been done, that's being done in the technology and systems and performance assessment, some of the case studies, tools, and so on, to show you where we are and where we need to be. And this will also be about policy. I think what's exciting to me about the events of a few weeks ago is we're likely to see, hope we're going to see some serious policy changes. And frankly, none of this is going to change at the big picture level in terms of energy use unless policy changes in a major way as well. So some of my slides to audiences that don't understand the climate change part, I spend 3 or 4 or 10 slides on this. I'm not going to spend any slides here. I assume all of you are familiar with the issues related to climate change and carbon emissions. My very quick summary is here. It's real. There is a scientific consensus about this. There are a few details to be worked out, but it's real. The uncertainties and unknowns are potentially dangerous. A lot of other countries have gone through this process and are doing things already aggressively. We seem to get sidetracked with drill, baby, drill. That's not a national energy policy. I think maybe we're now in a position to actually think about some more intelligent kinds of things. The policy picture, though, gets very quickly defined or driven depending upon your perspective. And here's the classic blind men and the elephant. Sort of everyone's looking at the generic problem and coming to the conclusion that there are different pathways. The pathway that's missing here, and that I'm the proponent of, and lots of others as well, obviously, is the end use side. I mean, we've in our lab we have a $600 million program to develop biofuels, which is great, and I hope they're successful. But where people miss is, where does all that energy go? Why are we building power plants, and why are we doing solar, and why are we doing biofuels? And a big part of the answer to that is energy efficiency in buildings, especially if you look at the carbon issue. Now, there are other options for carbon. There's a lot of interest these days in the nuclear side. I understand there's a big program here on that. There's some work at Berkeley. Little known part of my history is I was once involved in the nuclear field as well. So this is me at Newton High School, or actually Newton Junior High, one of the junior highs there. My first science fair exhibit was a building model of an experimental boiling water reactor. This is when nuclear power, this was what, in the 50s, early, I don't know, around 1960. This was when nuclear power was going to be too cheap to meter. So obviously I wasn't successful in this field, so I switched to energy efficiency. So let's talk about the picture. I think, let's see, got a pointer if I need it. So those of you that are on the building side probably know this, but it's surprising how many people don't understand this. If you talk about what the energy issues and problems are, people think about cars, I guess, first. But building energy use is the single largest end use out there. It accounts for about 40% of energy and carbon. It accounts for 70% of the electricity So it's a huge issue, and it's also the fastest growing area. By the way, I should also say that all of these comments are kind of as of a year or so, or the last 6 months or a year. A lot of things are changing in the building sector now, as they are in the rest of the economy. In the long run, though, these fundamentals aren't going to change very much. So if we then look at the buildings problem, we're back to the same issue of your perspective on this depends on who you are and how you look at the problem. And if you ask a utility person what the energy in buildings problem is, you get a very different answer than if you ask a building owner or an architect or an engineer. So that's a challenge, but it makes it an interesting challenge because there's lots of different ways to approach the problem. It would be nice if there was a silver bullet here. Do one thing and solve the energy problem in buildings. The answer is it's not possible. At best, you need, people have used the term silver buckshot. You need lots of different things to tackle lots of different parts of the problem. And that's because if you drill down and you break this 39% buildings into residential, commercial, you find that although there are a couple of biggies here, heating in homes and heating, cooling, and lighting in office in commercial buildings, the energy gets used in lots of different ways. And if you're going to tackle this problem, then you need to understand and then ultimately tackle many of these different issues simultaneously, in fact. So stepping back for a second, you sort of look at this building sector. It's diverse and fragmented. The way buildings get built is very complex. Lots of people involved in the decisions. There's not one person to go and convince, do an energy efficient building. There's dozens or hundreds. The decisions involve large amounts of money, long periods of time. It takes, a building like this might take 3 to 5 years from the time someone says, let's build it, to the time you occupy it. Lots of decisions get made there. And then there's lots of different subtleties in the sector. If you own or lease, if you own a building, the dynamics are very different than if you rent or lease it. Buildings are different by region and by type. Or restaurant is very different from an office building. The thing that unites all of them is that the potential for savings is enormous across all of these, which is good news. Now, there are lots of studies out there. There have been lots of studies for the last decade. A few recent ones, the McKinsey study, some of you may have seen. What this is doing is it's estimating on the horizontal scale the amount of carbon, which means energy that could be saved by various actions. And then it does an economic analysis on the left scale here of the cost. This happens to be in euros per ton of carbon, but dollars per unit energy, dollars per unit carbon. And what you see is rather striking. You see a whole bunch of things that cost you money. So solar and reforestation and carbon capture, all this stuff out here. It'll save a certain amount of energy, and it'll cost anywhere from $10 to $30 or $40 or euros per ton of carbon. Look at the things over here that are highlighted in green. These are the things that pay back. They don't cost you anything over time. And essentially all of these, almost all of these, there's a vehicle one in here, are things to do in buildings. So if you want to save relatively large amounts of carbon, 5 gigatons or 6 gigatons of carbon here, you can invest in energy efficiency in buildings, and the good news is it pays you back. So the sort of standard argument here, this is the low-hanging fruit. This fruit isn't even low-hanging. This fruit is on the ground, and it's been on the ground for so long it's actually rotting at this point. I mean, why wouldn't a rational person make these investments? You get like you can get 10, 20, 30% ROIs here. Why wouldn't a rational person do that instead of getting negative 20% on your local hedge fund or something? But this has been in place for a long time. McKinsey published this last year. Those of us who have been doing this for a while have published things like this for a very long time. So there's some, it's important to understand this, because when you talk about the technical potentials, they're huge, but then you scratch your head and say those potentials have been around for a long time. Why aren't we capturing them? And if we're going to do even more, then we need to be thinking about that clearly. Now, the good news is we've actually captured some of them. Here's the energy use in the economy. This is total energy use from the 40s or 50s here up to 1973. The blue line is actual use. So something structurally happened around 1973, for those of you that were old enough to know that was the first oil embargo. Had we been, if you look at the energy use per GDP, per unit GDP, had we continued to the current time period at that rate, it would have been the red line. But in fact, it was the blue line. So at current costs, we spend about $1 trillion a year on energy. We would have spent $1.7 trillion. So we're currently saving $700 billion a year because of the work we've already done in energy efficiency. The bad news is we just gave away that $700 billion to the banks, but that's an annual amount that gets regenerated every year. Now, where are we going in 2030, which is a convenient number? It's far enough out to do something and see some growth. If you project current growth, you get a 20 to 30% increase out to 2030. What people are arguing for, Kyoto says, let's get back to 1990 levels. California has a requirement. Actually, California has a requirement by our Republican governor that says to reduce carbon emissions by 80%. Actually, that's cheating a little bit. It's out to 2050. But massive reductions out into the future. So we did this for a while. We did that for a while. Now what we're arguing is we need to do that for a while. We've never done that before. Never been done in history. It's a big change. It's doable. That's the good news. The bad news is you aren't going to do it by business as usual. Now, so as a researcher, we said, well, do we have any models? Is there any evidence that you can dramatically reduce energy consumption by 30, 50, 75%? So let's drill inside a building and look at a refrigerator. Data on fridges from 1947 to 1973. That 73 number turns out to be a sort of pivotal number. Energy use per unit fridge, monotonic increase for all that time. Partly because they got bigger, but notice that the slope of this is greater than the slope of the increased size. This is amusing, too. Of course, if you extrapolate the size of refrigerators to about 50 or 100 years, they get bigger than houses. Fridges, of course, the real constraint, I think, is the size of a doorway in terms of what you can move through. Anyway, anyone want to guess as to, I'm going to pull away this blank piece of paper here. What does this curve do, this energy efficiency curve do? Does it rise? Obviously doesn't rise too much because it's off the chart here. Does it rise? Does it slow down? Or anyone want to hazard a guess? Some of you have seen this before, right? Dramatic reduction. Okay. Fridges today, a fridge you buy today uses about 20 to 25% of the energy for one that you bought in the mid-1970s. And, you know, that's a lot of R&D and good product development and good design. And then you say, okay, sure, but we did it by vastly increasing the cost of the refrigerator, thereby making them unaffordable to everybody, right? But look at the cost of the refrigerators. These are the costs. They bounced around in 1970. The cost has gone down in constant $1983, has gone down as well. So bottom line, we saved 3/4 or whatever, 80% of the energy use of this energy-consuming appliance, and we did it at lower cost. So simple question. If you can do it for a fridge, why can't you do it for a building? Why can't you do it for the whole economy? One of the reasons is that you say, well, how is this done? It wasn't done by innovative R&D guys saying, let's just do all this R&D and put it in the fridge and hope that you all buy it. A lot of it was driven by policy and mandatory standards, and I could do a whole talk on that. We have a big group at LBL that does policy. We helped develop the standards, the new appliance standards for DOE for the last 25 years, and there's 5 or 10 appliances like this. They're not all as dramatic. But what happened was the states and the feds decided they were going to mandate it because it was cost effective. They did it. They worked with the manufacturers, and that's the end result. So there's some interesting models here in terms of what to do. So now I'll switch from a fridge to a building, and let's talk about zero-energy buildings. Just to be clear about what I mean, and there's a lot of definitions out there. It's not so important to have a precise one, I think. We're talking about is not taking your current building and covering the roof with PV, but taking your current building and reducing its energy use by 60, 70, 80, 90%, drastically reducing it, and then with the remaining much smaller use, using PV or renewables in some way to zero it out. And it's a net zero. So in the middle of a cold, dark night in Boston, it may be consuming some energy, but maybe 12 hours later during the day, it's providing some to the grid. So it's net back and forth to the grid, using the grid as a kind of a battery, if you will. And I wasn't very particular. Is it 60% or 90%? It almost doesn't matter. It's a massive reduction and massive change in all buildings. So there's 2 schools of thoughts out there these days. There's what I call the dream here, which is some architects and engineers say, great, you know, I've done this once. I've seen someone do it once. Let's just go do it. Set the goal and go do it. And the argument is that actually we have the technology, we have the know-how, and let's just get off our duff and do it. The reality, I think, being a bit more practical after beating my head against the wall for 30 years, is that you can do it, but you can't do it at the scale and at the speed that you need in order to make the kind of changes that we need to see here. That it is technically achievable, but not pragmatically achievable at scale in the world that we live in today. And there's a whole bunch of issues that I'm going to talk about here related to people and decision makers and policy and so on. So the good news, again, is that if we set our minds to it and we push the technology and we deal with the policy issues and deal with the financing, we can get to those 2030 goals and do it. I'm just sort of making the comment here that I think it's dangerous to say it's easy, let's just go do it, because frankly, if you just let people go and do it, they won't, or I don't think they will, or I'm willing to put money on the table here that in 3 years or 5 years, I'll buy you beers at the local place, that there won't be very many net zero buildings out there. So one of the things we've done is a lot of modeling and simulation of individual buildings in the sector. This is a spreadsheet tool we put together to basically just look at the energy use efficiency or the energy use index of all buildings and the floor area and project them out into the future to look at energy and carbon. There's a lot of details here I won't get into. Look, this model works by building type, by vintage, and so on and so forth. Well, let me show you some results here. So here's a scenario, 2005 and 2030, where for each time period, every 5-year time period, we make some assumptions. So new buildings in the next 5 years are 40% more efficient than they are now. They use 60% of what they use now, and by the time we get out to 2030 here, they're 75% more efficient, using only 25% of what they are now. We also make assumptions about renovations and retrofits. We also make assumptions about the remaining buildings can put some PV on the roof. And again, this is a spreadsheet. You can play with it. So this scenario here generates this stock sector curve. So this is business as usual. It would have grown by about 25%. And in this scenario, we end up with a savings of about 30 to 40%. Compared to where we would have been today. And then this shows how the end use breaks down. The yellow here is solar. So with this as a model, we've done a lot of simulation and modeling. Oh, I want to make one more point here. So what does this mean? Here's a version of the curve I just showed you. The amount that we'd save in 2030 is roughly, this is a little bit cheating because it's compared to today's use, it's more than the entire output of the nuclear power plant fleet in the U.S. today. So we can save more in the next 20 years than the entire nuclear system puts out today. It's about half of all the coal-fired power plants in the U.S. today, and it's far more than all the hydroelectric, all the renewables, Three Gorges Dam in China, and so on. Now, China's interesting because as important as it is for us to do a good job in the U.S., if China and India don't do something similar, we'll never get our way out of the carbon problem. Here's some growth curves. In China, the U.S. commercial building stock is around here in square footage and growing at a pretty slow rate, 1 or 2%. The Chinese growth is up in the double digits, maybe a little bit less these days, but massive increases. And if these increases in square footage aren't done in a super efficient way, then we might as well start building the dikes now, I guess. And the same issues in India, more complicated. So here are those models I was looking for. So here we are now. Here's business as usual. This is the California 2020 goal of reducing energy use by 20% and the California 2050 goal of reducing it by 80%. And here's a scenario where half of all the new buildings built save half of their energy. That sort of seems like it might be plausible with some work. And every year we retrofit 10% of the existing stock with 50% savings. Again, I can pick anything I want here. We picked a number of them. We picked this one because it happened to meet the 2020 goal. But the reason I put it in was because this isn't all that aggressive on new construction. And if you then go out to 2050, new construction, which is the green, starts growing, and you end up out there actually at a higher level than you are back here. If you say, well, how do I meet the Arnold Schwarzenegger's 2050 goal, which is here, you need a scenario like this. And look at how aggressive this is. Buildings built today save 60%, and they save 90% by 2030, the rest being PV. And retrofits are 50% savings now and up to 80% in 2030. These aren't doable today with the cost and the technology we have. They could be doable in the future. But it gives you a sense of how aggressive you need to be if you want to meet goals like this, which is great. It's a target if you're a researcher or a business person looking for new market sets. Great. Now let's come back to the real world and look at what's really going on with real buildings. And this is the grounding part of this. So this is another scale. This is an energy use index scale. And I'm sorry, I'll be switching probably back and forth in units here, course of the day. KBTU, 1,000 BTU per square foot, is a metric all the architects and engineers know. The average U.S. commercial building is about 90 today. If everything was built to code and it worked, you'd be about 20% better than that today at 70. There's a bunch of interesting buildings, some of which have been monitored out at NREL, these 4 or 5 here, with measured energy use down around the 40. which is less than half of the current stock, which is good. And this net zero building, or the conceptual definition would say get it down to 10 or 15 or 20 and then provide the remainder with PV or wind or biofuels to bring it down to zero. So that's an interesting number. I'm going to come back to that in a minute. Here's a different way of looking at the problem as well. Here's the energy use by building type, or by buildings, and the number of buildings. And this represents the entire stock in the US of 5 million commercial buildings. This is a representative sampling, but indicative of the full stock. So here's the average is around here. Here's that 90 number I talked about before. And you see there's a long tail out here. There are buildings that use 3 or 4 or 5 times as much as the average, not unexpected. Some that use much less here. So what are we talking about doing? If I look at a building here, and you tell me you have a building with metered energy use of 230,000 BTU per square foot, I actually don't know if that's good or bad. If it's an office building, it's terrible. It's 3 times the national average. If it's a data center, it may actually be quite good. So unless you know more about the details of the building, and I talked about that issue before, you can't tell offhand whether these are good or bad. Here's that code requirement. This red line is where we need to get to by 2030. We need to basically shift the entire building stock by factors of 70 to 80% to the left. Again, very difficult to do, although plausible. So let's look at another population of buildings. Many of you know there's a U.S. Green Buildings Council meeting in Boston this week. They're out there pushing green buildings, and part of green buildings is energy. It's not the only part, but it's part of it. So they took 120 or so odd buildings that have been certified by USGBC at different levels. How many of you know about LEED ratings? Okay, most of you. You get certified silver, gold, platinum, depending upon how far you get up the curve. And here's the measured energy results of those 120 buildings. And the best ones are down around 20,000 BTUs. This is the number I used before, 20. Here's that 90, that average I talked about before, the average of the US stock. And there's some out here. So there are a couple things to note here. One is that about a quarter of all these buildings are worse than existing stock. That's not very good. About half of them, or the average of them, is about 70. But remember, 70 is where I said buildings would be if they simply meet building code. As soon as I talk to an architect and say, well, do you do energy efficient buildings? They say, yes, I design to the energy building codes. And my comment is, if you meet the building code, all you're telling me is that you've designed the worst building you're legally allowed to build. If it's any worse than that, you can't build it, right? The building code is a minimum. And so if you meet the building code, you've met a minimum requirement. There's nothing great about that. So the average LEED building is doing what theory tells you a code-compliant building will do. Probably that's a reflection on the fact that code-compliant buildings don't really meet code-compliant levels. But that's another whole story. So if you dig into this data a little more, a couple things come out. One is, here's those energy numbers again with my 91 highlighted there as a function of the type of certification. And this is good news. You see the people that try to get higher up on the LEED rating, the gold and platinum, are doing better, 50,000 rather than 60 for silver and almost 70 for certified. So this is generally good news. This is another interesting issue. I'll talk about tools later. If you look at the predicted, the design energy use, and then this is the ratio of measured. So here's design versus actual. So this is an important issue. If I design a building, do I actually get out in the output what I expect? And the answer, well, this is just a concept diagram. Here's the data. So if you were along this line, if all the buildings were along this line, then they'd be along this line here. What seems to happen with this collection of 100 buildings is the ones that have higher use, predicted higher use, actually ended up with lower. But all those ones where people said, gee, I'm going to come in at 30, 40, 50 at the low end, actually came in at 1.5 or 2 or 2.6 times higher than predicted. And there's a lot of reasons. That could be lousy design. It could be lousy tools. It could be great design, great tools, lousy construction. It could be all the way up and then lousy operations. So again, it's a fairly complicated thing. The reason I'm showing this is because in the end, we have to move away from hope and wish and prediction from tools and look at measured reality, and that'll be a theme I'll get to later. So I gave a talk a few weeks ago to some architects who are focused on the architecture, engineering, construction part, and the big missing piece here is operations. That if you don't think about and act on the operations part, we're never going to get to the goal either. And I'll talk about this later in more detail. We need measured building performance, we need the right metrics to track performance, and we need tools that operators can use to understand and manage the use real time. So what do I conclude from all this? We need massive reductions in buildings, and this net energy goal is probably a good one. There's a lot of data floating around out there, not necessarily in the right form, but it's useful to understand what's going on. We need to make this distinction between our intent and actual performance. And although the goals are, I think they're attainable, they're really challenging, and a lot of the last part of my talk is going to be about how do we then solve those problems. One other comment here, the same group, NBI, did a study of buildings that save 50% of their energy, and they found a couple hundred buildings that save 50% of energy, and there are 5 million buildings out there. So again, you can find examples, but you can't find very many of them. So this gets us back to, okay, we know we can do it. Amory Lovins, I think, once said that if it exists, it must be possible. So efficient buildings, zero-energy buildings are possible, clearly, but not at scale. So who's trying to sort of change the world here? Some of you probably have seen the Google take on the world. There are RE less than C, which is to produce renewable energy at less than the cost of carbon fuels. That's a great initiative. I hope they're successful. I think they're missing the big problem, which is buildings. But so how do we get to zero here? This is overly simplified, but I think I said this before. Cut the demand in half. I mean, sort of reducing it down to something that people can understand without being researchers. Cut the demand in half, satisfy the demand with double the efficiency, and then take the quarter that's left and deal with the carbonless stuff up here that Google will help us produce. So I think as a researcher, and I presume a lot of you in the research side, there's all these innovation challenges here, which I'll talk about in more detail. But I don't want to lose track of the fact that there are policy, economic, and political innovation. Again, I think we have a great opportunity here to be innovative politically in the next weeks, months, or 4 years as well. So I'm going to go through some of these issues here in a bit of detail. I always get asked, well, what does it cost to do a zero-energy building? Because cost is important in the real world. And the answer is, it depends. And so here's a simple way of at least understanding the boundaries. I'm picking 2 parameters I think are important. One is building size, small buildings and large buildings, and the other is climate. So as extreme examples, I'll take a small office building in Berkeley, California, mild climate, relatively easy to do a very low energy building, or a 1 million square foot high-rise office building with a data center in Houston with muggy, horrible, humid climate, big building, complex stuff going inside, 2 extremes. So if I say I want 70% savings, which is this green line here, I can get my 70% savings with modest increase in cost in the small building in a mild climate, a bit more in a large building in a mild climate, and then very expensive in a large building in a harsh climate. The other way of looking at it might be to say, let's take a number, $10 a square foot, that someone allows me to spend. Maybe Obama will decide to invest $50 billion in making buildings more efficient, and you could say, let's invest $10 a square foot in every building in the U.S. and push it towards zero net energy. Well, that will get me, and again, I've just made up the numbers. This is a conceptual diagram. That'll get me a 75% savings in my small building in Berkeley, but it'll get me a 10 or 20% savings in a big building somewhere else. So just in terms of thinking about cost, that's important. The other thing about cost is this one. Energy in the building sector is a $400 billion a year problem. But if you're a building owner and you look at the costs you face, that's what the world looks like. Energy is a 1% effect in terms of the cost of owning and operating a building, especially if you look at salaries. So what does productivity mean here? Now, some of you work for a living and some of you are students. I was a student once, so I don't mean that negatively. But if you get paid a salary in an office, take your office space, take your salary, multiply by 2 for the overheads that your employer pays, divide by the area of your office, and see what the number comes out to be. Sorry, just to be clear, this was a European version, so this is per meter squared, so divide by 10 for, well, maybe you work in meters, whatever you do. Anyway, just be careful of the units. So take your salary, multiply by 2, divide by your office space. That'll be a number, I think, like 3,000. If its number's much higher, then you're either paid too much or your office is too small, and if the number's much lower, then it's the opposite. But it goes to the point that if you do something to save energy and you reduce the environmental parameters in the space where you work and you reduce productivity by even a tiny fraction, you've blown it in terms of productivity. A 1% change here dwarfs or equals or exceeds the full cost of energy. The flip side is the part that I go for, though. If I can do something to improve energy efficiency that improves comfort, reduces glare, improves the thermal comfort, and I get any kind of marginal increase in productivity, even if I can't measure it, I've got a big dollar saver. So this is a point that people need to pay some attention to. So I've mentioned scale a number of times, and this is just a convenient way to talk about scale. There's things we can do. We can sort of look at widespread impacts and narrow impacts, and we can look at small savings or deep savings. So all of you know what ESCOs are, energy service companies. You can hire one, they'll come into your building, they'll pay to retrofit your lighting, and they share the savings. And they typically get 10 to 5, 10, 15% savings. You can do it in any building out there. The Clinton Climate Initiative is aggressively pushing it. Great stuff. But it basically has what I'm calling here shallow savings, but potentially very widespread. If you do a demonstration project, a zero-energy building today, almost by definition, is almost a demonstration project. It's one of a kind, big savings, but one of a kind. So we've got the extreme up here and the extreme here. We want to be as up here. We want large savings, but widespread. And that's sort of the theme here of, well, how do we do that? And so conceptually, again, what are the issues that you're faced with? If we're trying to get the sector down to much lower numbers, we've got this energy use per building times the stock times the changes over time. Those were those charts I showed you before. But if we look at this number here, how much energy the building uses, it's actually a pretty complicated intermixed set of issues. It's the owner and the budget and the type and size of the building. There's a set of issues there. The climate, location, and site. The design team, are they competent? Are they experienced or not? The technology you use, construction details, and so on and so forth. And it's this intersection of all these that ultimately give you that bottom number. And frankly, it's the weakest link in the chain argument. You need to do all of them. So if we want to create a future that's different for ourselves, how do we do it? Well, I like Alan Kay's point here that we don't just sit around and wait for market forces to do it. We need to invent it ourselves. And we're always told as researchers, as National Lab researchers, go out to the market and find out what the market wants. And we do that a lot. But you should do that with some caution, as evidenced here by this old Henry Ford quote, because people don't know how to ask for things that they don't know exist or don't know what the benefits are. If you ask a bunch of building owners today what they think about zero-energy buildings, they'll probably just not understand the question. So there's not a massive market demand for it, but I think we argued before by 2030 we better be heading in that direction. We have a problem. And it's not like there's no shortage of reports out there, all kinds of studies all over the world here, just a sampling of them, that talk about the problem, the nature of the problem, the nature of the solution. So here's the sort of simple 7 easy steps to a zero net energy building. Define the performance requirements, and this repeats on what I said before. Minimize the loads, supply those loads with efficient condition. Design for operation, that's a critical part. Don't design to hand the building over to an owner on day one, but design as if you were going to be there living in the building and thinking about how it's going to be used. The renewables part brings you up to zero net energy. And then the follow-on here on the operations part is monitor and measure the results. And as you learn things from here, as you invariably will, feed it back so the next time you design a building, you do an even better job. So I'm going to go through some examples here of systems and technology and some process issues that I think are relevant. It won't be comprehensive. I'd keep you here all night. But we'll just walk through some of them and sort of see what kind of lessons learned there are. Windows. So this is a 1973 chart from a window manufacturer saying, here's what the codes and standards want to do for buildings. Windows in 1973 were largely single glazed. They were terrible energy hogs, and people said, don't use them, and just a graphic representation of that. But in 30 years, we've basically cut the heat loss rate of a window by a factor of 2, and we can project ahead another 30 years and argue we should cut it. It's a factor of 3 or 4, but in fact, it's the delta between these that's the operative number. So we're going to cut it. We're going to save about as much energy going from here to here as we did going from there to there. And we'll get into this solar control part. So the good news is we've made progress in 30 years. There's a lot more progress to make in the properties of window systems. What kind of impact would that have? So here's, if you do a calculation of all the energy used by windows now in commercial buildings, it's about 1.3 quadrillion BTU. This is worth about $20 billion today. And by implementing a variety of technologies, existing technologies and future technologies. So here's where research comes. This is the stuff I could save about 1/3 of all the energy used in these windows by deploying stuff that we already have in place today. But I can save not only more, but I can actually get the window to be a net producer. And the trick here, of course, is these windows are providing daylight that allows me to turn off the electric light. So I basically reduce the heating and cooling to zero or near zero, and I now have a net benefit on electric lighting. And this takes me from a $20 billion cost to a $15 billion savings. These are annual numbers. The catch here is this is if I could magically change every square foot of every window in every commercial building. Not easily doable. On the research side, we have a portfolio of options here. If you're an architect or engineer sort of working at the level, I have a dimensional scale here of a meter of the facade of the building, shading systems. There are things to do at that level. There are things to do at the level of glass, glazing glass level. And there's things to do at coatings. There's a lot of R&D that goes on in coatings. And I'll talk about a little bit of that later. Very, very thin coatings that could do all kinds of sort of versatile functional things, all of which are designed to reduce energy flow and improve comfort. So here are the two big issues for buildings: insulation and dynamic control of solar gain. And what you want to do is make these windows much lower heat loss in winter, to the point where every window is what we used to call a passive solar window, where the sunlight on even a cloudy, or the diffuse daylight on a cloudy, overcast Boston day in the winter balances the conductive loss. You can actually find windows like this in Europe today, triple glazed windows with gas fills and argon, and you could invent vacuum and aerogel. This is R&D going on in all these areas now. The right window is climate dependent, and there are some cost issues. On the dynamic side here, managing the solar heat gain through the window, which adds to the cooling load, is critical, but letting the daylight in is important too, and I'm going to talk about these in more detail. So from a conceptual point of view, this is the loss part. Here's a net loss and a net gain. As windows get better and better insulating, and there's a time scale here that's approximate. So 60% of all the windows sold today are this low E window with it's an Energy Star window. And we're getting to the point we're getting to the point soon, I hope, where we're probably not quite there yet, where people will offer windows that are roughly twice as good as this window here. And that window in much of the US basically breaks even. It becomes a net zero energy window, in the sense that its heat loss and gain are balanced in the winter. This is the technology stuff that does it. I won't get into the details. More technology stuff. But the problem here, you've got to deal with glass coaters and window fabricators. There's a whole bunch of different players in the industry. No one company makes all these components. And part of the challenge is when you make a coating to convince the glass guy that the coating works, and then convince the window guy that assembles the whole thing that the coated glazings work. And cost is an issue with all these things too. The second issue is solar heat gain. On the one hand, you want windows to be transparent. You want the view, you want the daylight, you want the solar gain in the winter. On the other hand, windows are a huge problem with cooling load. Minimizing glare is important. And so what you'd like to be able to do is to control the sunlight and the daylight that comes through the spectrum, the intensity, the distribution. So the first one we do a really good job on. There are coatings on windows today. These are called spectrally selective cool coatings or glazings. They're thin film coatings. So these, again, are sub-micron thickness applied to windows. They're less than $1 a square foot. Every U.S. manufacturer makes them. And they take, this is the spectrum of a conventional clear glass, which is, so here's the solar spectrum. Here's the visible part. Here's the near-infrared part. Half of sunlight energy is in the visible. Half is in the near-infrared. This is clear glass that lets through both visible and infrared. As an extreme case, this green coating is one of these special coatings. It lets through almost 80% of the light in the visible spectrum and about 20% in the near IR. So this has a very high light transmission. It looks clear, but it keeps most of the sunlight out. And if you talk about the efficacy of a light source, the lumens of light produced per watt of energy, incandescents are way down at 17, fluorescents are 100, and daylight through this glass can be twice as good as the best fluorescent. And if we were more on the architectural side, we could get into the details here, but I won't. But the other problem is, so that's a good thing to do in most cooling-dominated buildings. We want to use that all the time. But the big issue here is dynamics, and that things change with location, with orientation, with season, with weather, with occupant, everything. So you really want something that changes dynamically. And there's something called a roller shade or Venetian blind that will do that. That's why they were invented. In a big building, you want to be able to do probably a bit better than that. The glass folks have been looking at smart coatings. Here's another material science challenge. This is old stuff in the sense it's been discussed for 20, 30 years. Photochromic glasses, you may have sunglasses that do this. Light sensitive, heat sensitive. These react to the environment. I want a coating that I can control. Actively controlled electrochromics seem to be the best option out there. It means I need wiring and power and control, but in the end, the benefits we think are worth it. There are some manufacturers beginning to offer the technology for automobiles and for cars. Here's some prototypes we built with one of those manufacturers showing going from the 60% light transmission to 3% light transmission and a good reduction in solar heat gain. We made this with a triply insulating window, so it was both a highly insulating window and a dynamic window. Again, unfortunately, much too costly to be affordable in anything other than a demonstration. Trying to build the business case for this, we did some modeling and simulation with some lighting software. So these are simulated images showing a clear glass, a tinted glass on a cloudy, a sunny, and two kinds of sunny day. And the bottom line is the electrochromic, which behaves like clear glass on a cloudy day, so it gives good visibility here as you get with the clear glass. But on a sunny day, you're able to manage the glare. You reduce the transmission by a factor of 2 or 3, and then by a factor of 10. You get basically good visibility of the computer screen under all conditions. And you can't see the screen here, and you really can't see it very well here either. So this is a technology that saves energy and saves cooling, but it also improves the comfort and productivity and visibility of tasks, which is important. So one of the challenges we've discovered over 20 or 30 years is if you're going to tackle a problem like this, like getting better windows in buildings, you can't just go out and invent a coating. You can't just go out and invent a tool. This is, again, a conceptual diagram of some of the kinds of things that we and others have been involved in trying to get these smart glazes into the market. So you do material science research. You work on the production side, because if you can't make them at very high rate at very low cost, they won't be cheap enough. We model their performance to assess how well they'll work. We build devices to characterize the optical properties, figure out how to put them into a whole window system. And then we get out in the field in both test buildings and real buildings. And even though we've done all this modeling and simulation and analysis, you've got to get out and find out what's really going on in the real world. We actually have a whole set of facilities that have been custom designed and built for these purposes. This is a GSA building in Oakland. We convince people, we charm them or convince them to let us use their building for a year or two. And we usually promise to return it to the condition that it started before. But anyway, this was a good experiment about 10 years ago. There were a lot of flaws with this particular product, but we learned a lot from it, and the new ones that have come out are better. I'm going to come back to some of this stuff in an example a little bit later. So the other big thing I've mentioned several times is daylight. Daylight is seen by all architects as something that's useful and great and important. But there are challenges with it as well. And there are technology-based solutions. Here's a Japanese company that's invented this elegant and extraordinarily expensive tracking fiber optic system that does deliver daylight into a building, but it's not remotely cost-effective. This is the real daylighting challenge for architects and engineers, is managing the light coming through a space, controlling the light levels with the ballast and controls and sensors. And this doesn't seem like rocket science, but after 20 years of struggling, very few buildings have systems like this that work. In 1990, we retrofit a 20,000 square foot building with these daylight dimming controls, and we made it work. So here's the energy use days of the year, energy use before, energy use after on the south and the north side. Interestingly, the lowest consumption, which is here, and the big savings are on the north side, not the south side. The reason being that on the south side, you've got this glare problem with sunlight. People close their shades and don't always open them when the sun goes away. So you don't get as much savings in this case on the south side as the north side. So this taught us some lessons about the need for smart shades as well. We think there's enormous opportunity in the daylighting area. A lot of the stuff that's being used today, well and poorly, is good old 19th century reflective and refractive optics. Nothing wrong with that if it works. but you need probably more than that. These are just examples, architectural examples and product examples of things that are designed to redirect light into buildings. The big issue also is to increase the amount of daylight, or the amount and usefulness of the daylight in the perimeter, and then bring that perimeter deeper into the space. And it's a real challenge to do it with the materials we have today. There's a lot of interesting work that's been going on at a fairly low level in terms of new types of optical materials. One of the big challenges there is how do you characterize them. Marilyn's lab here at MIT is doing some of the leading work to try to solve that problem. If a manufacturer puts out a brand new material and you can't characterize it and tell an engineer how to simulate it and predict its performance, they aren't going to adopt the material. So this is a critical part of the big picture here. And for those of you that are in the material science area, there's all kinds of interesting opportunities. The scale here, this is a red blood cell. So this gives you the scale of these microstructures. They aren't quite nanostructures, but microstructures that could be used in various ways to control or redirect light. But the bigger picture here is this integration issue with the, again, a concept diagram of a perimeter office here where you've got the glazing and the shading. You deal with comfort. You're dealing with lighting, maybe a special glazing to let the daylight in, maybe some PV here. And we're connecting this now to the grid and the utility to make sure that we're managing energy use here in a way that not only makes sense in the space, but makes sense in the bigger outside world. Gets you into the interesting issue of what are the right metrics. Is it energy? Is it comfort? Is it dollars? Dollars may not correlate with energy depending upon the utility rate structure. Is it carbon? And this gets us very much into the controls issue. So what we want conceptually is this. So I mentioned before that the building we did 20 or 18 years ago, people manually operated the shades and the blinds. There's nothing wrong with that. I work in an office with a manually operated shade, and most of the time I'm smart. Actually, I'm not smart enough to operate it to save energy, but when the sun comes in at 3 in the afternoon and I can't see my computer screen, I get up and I adjust the shade. So what we're looking at here, again, conceptually, is stuff that will do this ideally automatically, reliably, cheaply. These smart controllers deal with the window system, the lighting system, and they have to be smart enough to deal with task requirements and preferences and conditions and weather and so on. This is actually not a trivial challenge to make it work, and not just to make it work once, but to make it work reliably at a building level. And the other question is, if we get into controls, and I'm emphasizing this because I know there's a lot of interest in capability at a place like MIT, there's the engineering side of controls. How do you make something that maintains a light level? That's relatively easy to do. How do you make things that adapt automatically without getting a technician back into the space to reprogram it and to change the optics and do this and that? And how do you get something that adapts to user behavior in an appropriate way? Those are interesting research challenges. This diagram actually came from some colleagues of Marilyn from Switzerland who are looking at this problem and having some success. This is a facility we operate to test these facade systems. We used to have the electrochromic coatings here. Now we're testing automated blinds and shades. Some of this is about the engineering performance of the shades and blinds, but some of it is about how people use and work in the space and what they think about the environment inside. So we're trying to do both of these at the same time. These are off-the-shelf units procured from Europe that where the bottom, I mean, here again, this is not rocket science. This is a blind system that blocks glare on the bottom but has a different slat tilt here and lets light in to brighten the ceiling and allow the lights to be turned off. Conceptually easy, hard to find in the market, hard to control. Let's see if this works. Here's a technique called high dynamic range imaging that's working there, showing the brightness patterns in the space correlated quantitatively here over a wide dynamic range. And these blind systems tend to pump the light on the ceiling where you want it. The window tends to pump the light down here, which tends to create glare on the computer screen. So a lot of what I've just showed you is kind of the research lab side. Does any of this stuff work in the real world? And so we get involved in projects. I'm going to show you an example of a project here with that. One of the big issues there is cost, though. And I just want this one slide on cost first. So here's the classic view of cost. Here's that room with its stuff. And I'm going to add a bunch of things to it that increase the cost, the smart shades, the daylight dimming. And I'm going to reduce, hopefully, the heating, cooling, and lighting. And I take this annual savings and divide it into the first cost, and I get a payback. The interesting thing, though, is that the decisions I make here impact the peak cooling load, which impacts the chiller size, which isn't free. I'm the owner. I'm paying for the chiller. And the chiller then creates incremental demand on the utility grid, and someone's paying to build power plants out here. So if I can somehow get the cost trade-off to be on the full screen and not just in this blue box, if I now do an aggressive electrochromic coating or automated shading system here that reliably reduces the cooling load, I can make this smaller, and I can make that smaller, and I can somehow then try to figure out a way to take the dollars from here and the dollars from here and put them back here. So that's the challenge. It's hard to do because most engineers won't do it because they don't believe that all those systems will work reliably, and they don't believe it with good reason, because in many cases they haven't. So here's a real building. This is actually an artist's sketch of the building before it was built. The New York Times, if any of you are in around 41st and 8th Avenue, New York, this building's up now. They commissioned Renzo Piano, a well-known European architect, and a good team of people in New York to build them a brand new 1.5 million square foot building. They decided to make it an all-glass building with some external shading for a variety of reasons. Well, to get into they wanted the city to see how news is made and so on. They came to us and said, look, we've got all this glass. We know we have a lot of daylight, but how do we control glare? How do we do the cooling load stuff? How do we make sure people can see their computer screens? And they went to their consultant and said, give us an integrated system that will do all this. And their consultant said, A, it can't be done, and B, even if you could do it, you couldn't afford it. That's why I mentioned the cost issue before. So they had actually seen some of those studies I just showed you before that we had done and came to us and said, what do you think? Said, you've done it. Why can't we just do what you've done? And we said, well, we did it in 100 square feet. You want to do, or 500 square feet. You want to do it in 1.5 million square feet. There's a bit of a difference there. But we agreed to work with them. And what we did was we convinced them this was complicated enough they should build a test bed. They built a 5,000 square foot test bed in New York. So here's the floor plate of a building. This is the 5,000 square foot piece that they built. We completely outfit it with a series of different dimmable lighting systems, motorized shade systems. They put in 3 or 4 furniture systems, all kinds of stuff. We developed a bunch of new instrumentation, not just to measure the engineering parameters, but to measure glare on the computer screen and a bunch of other things. And we did this for, well, 12 to 18 months. And I want to comment here. I probably should have said before, most of our work is supported in the public sector, the U.S. Department of Energy, the California Energy Commission, and it's organizations like that that have been investing with us and others for a long time to make these things possible. And in this case, NYSERDA, the local energy agency in New York, did it. Out of this, rather than just picking a winner, we came up with a performance specification to bid into the marketplace. The other thing was we did that testing in this mock-up on one corner of a parking lot. Then we said, well, what about the other corners of the building? What about the height of the building? So then we switched to simulation. And this is a program we developed called Radiance, which is a lighting simulation tool. We got a 3D model of the downtown urban environment. We inserted our prototypical floor here at different levels. And then we simulated the view sitting in an office chair in 18 different positions around this floor at 22 different positions over the course of a year to figure out when and where the shade should be pulled, how dense they should be, and so on. Here's an example of the identical view on floors 3, 6, 12, and 26. On the lower floor, you've got a lot of buildings across the street blocking some of the sky glare. By the time you get up to the 26th floor, you're seeing a lot of sky. This is a 52-story building, by the way, but the Times only occupied the first 26 floors. So we used field tests to do the integration work. We used a lot of simulation and modeling here. Lots of other innovative things were done in this building, but the job wasn't done. So then we bid it, and by the way, the cost came back at 1/3 the cost that they'd been quoted originally on the dimmable systems because of the work to be done here. But this is a complicated system, so we also built a commissioning system so that they could install it and calibrate it right, and delivered that, a little cart with some technology, to the owner. Here's the final building in operation. Shades are pulled, the lights are dimmed or turned off. Seems to be working pretty well. We're trying to get back in it and do some measurement there now. I think I'm going to skip some of those details. A lot of debate going on about glass buildings. I don't know if the architects in the room are into this or not, but the architects are using a lot of glass in buildings, and a lot of the rationale for it is green and energy savings. Not always clear that that's the case. This is the way I sort of think about this, is that you can do glass to just meet the code, and there's not much thinking to do the code. It tells you what to do. There's a broad middle of the market where there are somewhat prescriptive packages, but medium-sized or modest-sized windows, double glazing, spectrally selective glass I talked about before, some type of simple operable interior shading, some type of simple on-off light controls. If you're going to do lots of glass, highly glazed buildings, then in my view, You need to do a much better job on the tool prediction part. You need to make sure you've got all these things integrated. You need some form of dynamic smart control on the shading. Certainly capture the daylight, the dimmable part here, and make sure that you're dealing with people as well as energy. This takes extra time and money, but I think it can deliver a product that will really work. Lighting. Just a couple slides in lighting. Lighting uses a lot of energy. It's the single biggest end use in commercial buildings. These are details about where it all goes. I won't bore you with them. The theme in lighting today is get better sources. How many of you have heard of LED lighting? Everyone's heard of LED lighting. It's promoted as the most efficient thing out there, right? Okay. Well, it is getting to be much more efficient, and it will continue to get more efficient. It's also very expensive, and most people don't believe it will be an option for overhead lighting for another 5 to 10 years. It's great for task lighting and other small things like that, but it's very expensive. And what we're trying to do now is save a lot of energy in the next 5 or 10 or 15 years. So what we should be doing is paying a lot more attention to controls. You should be using light only when you need it, where you need it, and so on, and meet the user needs. Sounds pretty simple, but it implies a controls infrastructure, again, that doesn't exist in most buildings. So we're arguing is that lighting should be dimmable and addressable. You should be able to communicate with and talk to any light fixture anywhere in the building and tell it to control its output. If you can do that, if you have the enabling technology to do that, then you can implement any strategy and change those strategies over time. That's interesting. My machine just told me that PowerPoint quit, so let's see what happens. Hasn't happened before. Any questions while I'm trying to figure out what's going on here? Maybe. Yes?
In Europe, there are efficient standards called Passive House and Minergy. And for the last 3 or 4 years, Passive House in Darmstadt has included in their conferences a couple of tracks on extremely high performance retrofit, gut rehab retrofit. Where in the United States is gut retrofit energy savings efforts to save 50 to 80% going on today?
I don't think you're seeing any major programs with that. I do think there are individuals doing things like that, but not at the programmatic level. I think those are the things that potentially might be implemented in terms of new initiatives for new administration. I think the issue of, are the pieces in place to do that? There are some groups out there that have the smarts to do that. I'm going to, hang on one second, I'm going to try this a different way. It's just frozen in a... How about more questions while I... Oh, there we go. Okay. Oops.
Yeah.
Sorry. Yeah.
Does it work? Yeah.
Go ahead.
So I also come from Europe, and we're starting to implement in Germany certification for buildings that is mandatory.
Yep.
Is there anything like this coming up in the United States?
Yeah, there's even stuff coming up in my slides if I can get to it, but I have some examples of those German slides. There is in California. Okay, I'm going to go to the restart mode here. Let's see if that works. PowerPoint not responding. Force quit. Okay. Whoa. Sorry, I never done this before. Force PowerPoint to quit. Okay, I think I get it. So the answer is, in California, they're mandating all new buildings starting next year have to post their energy performance. And And that should lead us in the direction of that direction. We actually brought over some of the European folks who are doing that in the UK to help California design that process. Recovered file. I don't think I want the recovered file. I think I want the original file. And then I want oops. Just do it the old-fashioned way. I'll just jump to that. Sorry about that. That's not happened to me before, but I guess if you give enough presentations for long enough, then. Okay. There you go. There's the whole rest of the talk. Anyway. It's actually, I hit the button. I'm done. Sorry about that. Let's going to go back to, okay, so I just talked about, there are a couple slides here about the grid, and I talked about lighting. I finished that. The grid is important. We want to connect to the grid. We want to be able to manage buildings in the grid. I'm going to just cut through a few things here. We've been running a DR program, a demand response program in buildings for some time. And again, the theme of getting out and measuring things and making them work in real buildings, showing that if you set it up right, when you want to shed 5% or 10% of the load, you send an internet signal, an XML signal, and it responds. And the idea is that tens of thousands of buildings will automatically respond. The owners figure out what to do here. And this whole interesting issue with the grid of how do you manage it in different time scales. And there's a lot of work going on around the country for this. There's a lot of talk about smart grid stuff, which is relevant here. Talked about operations of buildings. There's all kinds of issues in operations. You've got a group here in architecture, Leon Glicksman and Les Norford, who are doing work in this area. Important, interesting area. Fault diagnostics and self-tuning. Again, if we're going to add all these new sensors and things in buildings, we need to make them better. So here's this, your question about what's going on in Europe. A lot of benchmarking of buildings. I won't get into the details here. Here are the certificates that the Europeans are using, and we're going to do something like this. The main point here I want to make is that you have to distinguish between an asset rating, which is as designed and built, and an operational rating, which is how people use it. And I think that's a critical piece of the whole puzzle. If you don't do that, you potentially can be in trouble. So we're aggressively moving in that direction. And if you then backwards, here's a case where they predicted the lighting energy use would be 14 and the actual was 43. And it turns out that there's a bunch of different factors, all of which influence that, and you need to understand that at some level of detail. So that's where we think things need to be heading. California spent a lot of money building a big database. We have access to that database. We've developed a new tool. You can look it up here, energyiq.lbl.gov. It allows you to explore performance characteristics of buildings, and this tool will be used as part of that energy cost thing. I showed that one before. I'm going to skip this system stuff. Here's another example of working with a real owner to implement some things. This building has no mechanical cooling and 12 floors. That's unheard of in the US. Class A office building, a GSA building. It relies on openable windows that are automated and an exposed concrete ceiling, and it's San Francisco. The cool night breeze blows over. We did extensive modeling with CFD and with Energy Plus to convince the owner that there would only be a few hours per year when the comfort conditions in the space would drift above the required levels. But based on that extensive simulation, they went ahead and designed and did the building. There's an interesting question of where it stands now. I think it seems to be working pretty well. We're in the process of going back into it to understand in more detail. One of the things we did was we coupled a real control system from the building with a virtual model of the building before the building was built to work out the bugs which we knew would exist between a sophisticated control system and the software. This gets us into the whole issue, which again, I'm saying this in several different ways. We need to think about the life cycle of the building. Too often we spend time on the design side and think that when the design is done, we're finished. But the construction, commissioning, operations, occupancy, and you're handling lots of data here all the time. So I don't know how many of you have heard of building information models, BIMs. A few people. This is another one of the up-and-coming both buzzwords and realities. A little bit like green. It means lots of things to lots of different people. There's a whole organization out there called Building Smart trying to develop standards for BIMs. But the idea is that you specify everything in a sophisticated model so that the engineer, the architect, the facility manager, the construction guys all work off of the same building data model. And there's some stuff here in tools that I'm going to skip for time purposes. But if we're going to do more sophisticated buildings, we need more sophisticated tools. And we've been active in that area for a long time. So the last few slides here. One of my themes is that we need a package of solutions here: technology, policy, process, and markets, if we're going to make or if we're going to achieve this zero energy problem. I'm going to make a big pitch here on the policy side. And policy comes in lots of different flavors: mandatory, voluntary, Energy Star programs. You've all heard of Energy Star programs. There's a voluntary. The LEED rating program is a voluntary program. Lots of different scales. It's actually good to try things at a state and local level first and make your mistakes and fine-tune it there rather than launching it nationally and sort of finding out that it doesn't work. The issue here is transforming markets, and how do you do that? And here's a scale of energy performance. And again, standards tend to bring up the bottom. Voluntary standards here, labels and ratings, subsidies and incentives push the front end of the market, the innovators, the leaders, and R&D kind of makes new things possible. So there's a whole array of tools that we have for doing that. And the question is, does it work? Well, here's some data. I'm a transplanted Californian, so I'm not just tooting the horn of California. But here's energy use per person in the US and energy use per person in California. California's had an aggressive set of policies to manage energy use. And there's a lot of other things going on here, sure, offshoring of stuff and so on, but it's clearly worked. And another way of looking at it is look at different states. Here's the US average. Here's California, just because we've had an election. This is from 2004, but if you plot the red states and the blue states, guess what? So I'll leave you to interpret that. The Public Utilities Commission in California has mandated that buildings will be zero net energy in 2030, and they're trying to put in place the infrastructure to make it happen. They realize you can't just say it. They spend about $1 billion a year, which is a small tax on electricity, to run this program. One of the things to be careful of, sort of what to do and what not to do. What we currently do now is in California, there are 11 different programs out there that, for commissioning and retrofit, and Title 24 is the standards and LEED programs. You just confuse owners and decision makers with all this stuff. You basically need one big program, which is figure out what you want to do, integrate it, get it right, and do it. Obviously, I'm oversimplifying here a bit. But all these things can fit comfortably within these programs, which works both for new and existing buildings. So the grand challenge here is to look at the life cycle, look at integrated systems, do the technology plus policy piece. And again, I assume many of you are interested in the research and innovation side. The important point to make here is that innovation and research isn't just about the technology. It's about reducing risk and reducing cost and time. And in the building sector, these are huge. Most building owners will tell you in a heartbeat they would far prefer to have a slightly less efficient system that costs less and works well all the time than something that performs better, and who knows if and when it will work and how much it will cost. So the sort of set of bottom line questions here, or bottom line directions here, I'll emphasize here. I think what we need to do now is try a bunch of things. We don't know all the answers. Go out and try things. If it works, deploy it widely. If it doesn't work, fix it and deploy it. Be experimental in terms of policy and focusing more on the ultimate decision makers, the owners and the operators, and thinking about scalable solutions here. And frankly, I've often heard this being described as we need an Apollo moon mission or Manhattan Project thing. I think that's the wrong model. That's a classic engineering model. I realize I'm in the heart of engineering here, but you put enough smart engineers on getting to the moon and give them enough money and you can do it. This is more like eradicating polio or dealing with something like that. There's a technology component to it that's essential, but if you don't get the rest of the infrastructure in place, it's not going to work. So it's a win-win. We can make people happy in buildings, we can make owners happy in buildings, and we can help save the planet at the same time. Thanks. And apologies for the little rough spurt there, but yes?
Doctor, when you helped the New York Times build its headquarters, did you essentially create the monster that ate New York specifically because they now have a metric so that if anybody intrudes with their other real estate project, that they now have a metric that can show exactly how much your new building is going to cost their efficiency? And now do they have a legal right to either sue or where we have a carbon credit system where you use your efficiency law, you'll take the efficiency loss, but the other developer has to buy that loss, or the right to give you that loss?
I think I missed something on the developer side. What's the loss part of it?
Well, if I've got the New York Times building and I've got all this efficiency with the blinds and everything,
Right.
and then you put another building across the street from me and thereby intrude on my
I see.
ability
Sure.
to achieve that efficiency, do I have a legal right and do I have a huge advantage in court and in the real estate industry to really pound you
Yeah.
good unless you meet my demands?
Yeah, if you look at the zoning laws in cities around the 1920s, 30s, 40s, those were big issues. That's the reason why if you look at New York buildings, you see these staircase-shaped buildings, right to light stuff. I haven't followed that recently. I don't think that it would be a big issue in court. They are building a 40-story building adjacent to the New York Times. The building is designed to be relatively efficient. The amount that this stuff would change would probably be relatively small. If you put a huge investment in solar panels and PV panels, and you were then to build a building adjacent to it to completely block them, that would be a huge economic problem. Their output could go to zero or near zero. So I could imagine that being an issue. I don't know how that's being dealt with. I'm guessing it's on a jurisdictional basis, and this is the kind of thing that people worry about now in terms of investing in this, especially in an urban area. But I think it is an issue, and probably people that know more than I do probably need to get engaged. Other questions?
You mentioned that things need to happen on a regulatory and policy. Would you advise trying to get action through taxing, changing the economics, or trying to get various regulations passed? Which do you think would be more productive?
Well, I think it's not an either or, it's a both and. So most of the appliance standards I mentioned before are done, the law that enables them, which actually started under Reagan, was that they needed to be cost effective. So the way the law works is that you tighten up the standards for the fridge and you're forced to buy a more expensive fridge, but it saves you more energy than you pay. So it's basically guaranteeing you that the extra money you invested gets paid back. So you could do a lot of things that way that in the short term people might pay out more, but in the end they would get back more. So it's sort of a forced savings account if you want. Personally, I mean, what we do in California is there's a tax. It's a fraction of a cent per kilowatt hour, and that tax goes into that billion-dollar fund, which is going to push all these other things forward. So it depends on your philosophy. I think these things need to be done, personal views, And I'm not averse to paying a bit more at a collective social level to see that they get done and get done effectively. I don't believe, for a variety of reasons, that market forces alone will get us where we need to get to. So I'd go back and say, what are the options? And you mentioned two, but there may be 3 or 4 or 5 more. Maybe incentive credits to owners, or incentive or tax credits to manufacturers, a whole variety of things that one can do. And you could look and say, what's the mix that gets us fastest and cheapest to where we want to be? There's a comment beside you.
Your talk has been mainly about, has been solely about commercial buildings. Do you have any comments on residential and what the Pareto is in terms of the gains you could get from residential?
Yeah, we've done a fair amount on that also, just too much to talk about. In general, the issues and the opportunities are the same. I think residential is easier. It's easier. There are a number of folks around the country who are building net zero energy subdivisions of 50, 100, 200 houses. And I'm sorry I didn't completely answer the question about the passive house, but there's there's all these projects going on in Europe as well. So it's clear that that can be done a lot more readily. There's also this huge range in, I mean, coming from California, but Boston's in the same league. You know, you pay huge amounts of money for a house here that you'd pay half of for if you, or just to here if you go 20 miles out or whatever. So the whole issue of cost in the residential environment is a lot more discretionary. We spend a lot of our money buying things that are discretionary, and you could argue that if efficiency and carbon and all that become societal benefits and of importance, then people will simply, you know, put less marble in the kitchen and put more PV on the roof. I have a neighbor who did a solar PV and solar thermal and bought a Prius, and someone said to him, well, you spent a lot of money, didn't pay back. And he said, yeah, but my neighbor bought a Mercedes. And he said, I spent less than my neighbor did, and he got the Mercedes, and I got the Prius, the PV, and the solar thermal. So we basically shouldn't, for about 2/3 of the country who have the wherewithal to spend the money, it's a discretionary, value-oriented proposition on the residential side, I believe. And if people just decided that was the right thing to do and useful to do and it was worth it collectively, they could do it, and you wouldn't need all this mandatory this and that and everything else. So I think the market drivers are a bit different, and I think more complex, actually, more nitpicking and more financially oriented on the commercial side, which makes it a bit more challenging. But they're different. They're both challenging. They're both opportunities, and there's certainly stuff to do in both cases. Oh, sorry, back over there.
The 2007 Energy Act created a new center or initiative for zero buildings, and I'm just wondering how your work in the Lawrence Berkeley Lab ties into that, and whether you see that eventually trending toward mandatory requirements as opposed to these goals for zero.
There's a couple elements of the Act. For federal buildings, it mandates GSA and other federal agencies to sort of move more rapidly towards these goals. And the numbers are different. I think the DOE numbers are zero energy by 2025. They're actually, there's not a lot of detail there. And so if it says zero energy by 2025, it doesn't say that every building shall be it. It sort of talks more about the enabling stuff, that it should be possible to do it. What's different, I mean, in a sense, the feds don't control what gets done on a local basis. In California, the PUC is able to put out mandates or requirements that must be met. In California, you currently have to meet a building code, and that building code tells you what you must do. You can't build a house in California. So the code stuff tends to be state and locally driven, which is probably good. So I think you should look at the federal national one as reinforcing this trend, but not, you know, driving down to control what each person does in each state. At the research side, one of the things DOE is trying to do is to put more funding into the national labs and universities and other groups to collectively support all this. And they're stuck now because although the legislation was passed, there's a continuing resolution that holds up the funding, and they don't quite know how much they're going to get. But it's been a big increase in the work that's been going on in the buildings area. We hope it will continue. There's also an interesting question of what the right mix of short-term versus long-term is, and I think they're sorting all that out as well.
I think your questions on risk, or your statements on risk, were particularly cogent. And as the VP of Finance of a local university said, we want to be near the cutting edge, but not so near that there's blood involved.
Right.
I think that the question that I have is, what is the role of universities or of building owners who own multi-building campuses, and how much leverage do they have within this situation as opposed to individual building owners?
Great, that's a great question, and it's one that we're engaged in too. First of all, I think the universities around the country have taken some of the lead here. There is an organization, maybe you know what it is, of university groups for sustainability. I don't quite know the title, but quite a number of them have got together and set their own goals. I'm on a committee for the UC system, the 10 UC campuses. They've required that all new buildings, actually a year ago it was all new buildings should be LEED Silver, now it's all new buildings should be LEED Gold, and so on. So they're beginning the process of doing that, and the individual facility managers or campus managers are actively engaged in doing this. Now, the interesting question is the university system making more funds available for them to do that? And I'm not sure what the answer is. I think the answer is no. They just have to struggle with all the things we talked about here. But I think there are huge opportunities on a campus basis. I think deploying things like chilled water loops and thermal storage. The UC system set up a new campus in Merced, which is in the Central Valley. It started as a greenfield 5 years ago. There's now a couple million square feet. They have a 2 million gallon storage tank of chilled water. They run the chillers at night, so they pull them off the daytime peak, chill the water down, and then circulate it during the day. We have a contract from DOE and the state to take a careful look at that campus, and it's already doing pretty well, but to see how much better it can do. Its goal, by the way, is to use half the energy of the other UC campuses. The other interesting thing about universities is you have a lot of laboratory buildings, data centers, special use buildings, which tend to be enormous energy users. And there's a lot of work going on at our place and other places on buildings like data centers to make them much more efficient. We're building a supercomputer center that we're going to try and build without a chiller system. I don't know if there's any in the world that currently operate without chillers, because these computers use megawatts of power. They run hot, and well, they don't run if they get too hot, so how do you cool them? Well, the way they cool them now is with chiller systems. Half of the energy in a data center goes into cooling, half goes into the computers. We're in a climate that makes it possible, but we're going to try to do it without chillers. So there's a huge opportunity, and there's a lot going on already, and I think it's great to see the campuses taking the lead, and hopefully some of the rest of the private sector will follow some of those models. I'd be interested in hearing more about what folks at MIT are doing, in fact. This one in the back.
I guess I have a question about finance, if you have any thoughts on this, kind of following off of the question of what is the role of universities. I'm wondering, how do we get this done, and how do we convince people that there's money to be made in this too? And what's the role of large institutional investors, like endowments, pension funds, that sort of thing? Okay. Do you have any thoughts on that and how that relates to
Sure.
buildings?
So it clearly will take money to do all these things. It's interesting, again, I would joke before, but the government seems to be in a mode now where they're willing to spend public money to get things done that seem to be important societally, and if this is deemed important, maybe it becomes an option. It is interesting that we claim with some data to back, well, the other thing is, well, how do you get people to do it? You need convincing data. In principle, again, if the free market works, markets work if they have good information, right? So if you've got good, sound information that this stuff works and pays back, then a smart, MIT-educated, Sloan School financial manager should invest, right? So the question is that happening, or how much is that happening, or why not? And obviously around the country, it hasn't been happening. I think it's partly a data problem. It's partly it's not sexy or elegant or cool, compared to the other things people invest money, or at least it hasn't been until now. So maybe projects that establish the validity and the power and the value. But these are things, again, that look like they're 15, 20, 25, 30% ROIs, and you would think, especially in the environment we're in now, that people should invest. One possible thought is maybe the Fed should do what they're doing with the banks now, not so much buy those contracts, but guarantee the risk behind them. So if people aren't making the investments because of the risk, and we can demonstrate that the risk is known, quantifiable, known, manageable, and then the government will stand behind it. Maybe that's an option too. I'm not a financial guy, so I mean, I read and think and talk to people about it. The bottom line, I think, is there's plenty of opportunity to be as innovative in finance and policy as there is on the technology side, and there are a lot of people that would probably argue that we'll get further faster on that side. Again, I'm going to argue it's both. It's not an either-or proposition. Frankly, the stuff that's out there today, the proven stuff, you shouldn't need. There shouldn't be big risks. You shouldn't need massive changes in the financing. If you want to build buildings that are radically different than they are now, then you've introduced risk, and then maybe there's other mechanisms or modes there. So lots of opportunity on that side as well. So I'll figure out a way to post this and let Marilyn know, and you can communicate to this group if that makes sense.
So there is a reception